7 on limit properties and techniques. So first example here says, find the limit of the function k as x approaches a. So I'll call this function f of x, and the function is f of x equals k. So whatever I plug in for x, if I plug 1 in for x, I get a y value of k. If I plug 2 in for x, I get a y value of k. If I plug in any number for x, I'm always going to get a y value of k. So as x is approaching a, if I plug in a, I get k. If I have a plus 0.001 or a minus 0.001, I get k. In other words, this value is going to be k. As a graph, this would look like a horizontal line. No matter what x is equal to, the function value is equal to a y value of k. For example, the limit of x as x approaches a. So if I say that f of x equals x, what does this come out to? So if I plug 1 in for x, I get a value of 1. If I plug 2 in for x, I get a y value of 2. Whatever value you plug in for x is the value of the function you're getting out of it. So if I plug a in for x, I get a y value of a. If I plug in something slightly less than a, I get something slightly less than a for y. If I plug in an x value slightly greater than a, I get a y value slightly greater than a. This function looks something like this blue line we have here, y equals x. And so no matter where x, wherever a is at, it could be to the left, or it could be to the right, here's my x value of a, my y value is a, and it's approaching that value from both sides, so this one is a. In the next line, I have a few examples. As x approaches 2, the limit of 5 would be equal to 5. The next one is 5, and the last one here is either. All examples from what we have. Next example, we have the limit of f of x as x approaches 2 is equal to a, and the limit of g of x as x approaches 2 is equal to b. So we're going to do some arithmetic with these different functions. And I have all the answers in here. I would encourage you to try these first, check your answers with what I have, and I'd encourage you to do that for all the examples that we're working through here. I might go at a faster pace or a slower pace for you, but work at a pace that makes sense. And you can listen to my explanations. If it makes a lot of sense, maybe you can move on without those. But here are example or answers for these few different examples. And we're using those two limits of f and g, and both of them are as x is approaching 2. All right, so limit techniques. Let's go ahead and try this first one. The first thing you want to do is direct substitution. In other words, plug it in. If you look at this function we have here, this function is continuous, which is really nice for a limit. In other words, I'm not exactly sure what the graph looks like, but there's no values of x where we're going to have any holes in the graph or where we'll have any discontinuities. In a fraction like this, there's nothing that could ever make the denominator equal to 0. So the graph could look like a lot of things. Let's just say maybe it looks something weird like that. I don't even know. But as x is approaching 5, since the function is continuous, I know that the limit as x approaches 5 is going to be the same as the value of just putting 5 in. So if I plug it in for the numerator, I get 0. If I plug it in for the denominator, I get 26. 0 over 26 is equal to 0. For the next one, now this function is not continuous everywhere. In other words, if I plug an x value of -1 in, I would get -3 over 0. So at x equals -1, the function is not continuous. So the limit as x approaches -1, it might exist or it might not. I'm not sure. But at x equals 4, it is going to be continuous. There's nothing weird going on around where x equals 4. We're just going to plug it in for the numerator, plug it in for the denominator, and we get a value of 12/5. So direct substitution is what we want to do if at all possible. Sometimes, however, we get something a little bit strange. We get this indeterminate result of 0 divided by 0. Now, 0 divided by a real number is 0. That's fine, as long as you're not taking 0 divided by 0. Those don't just cancel each other out and give you something different. It's an indeterminate form. We can't evaluate it. This just doesn't make any sense. So in our first example here, I would try direct substitution. And if I plug 3 in for the numerator in this original numerator, I get 0. And if I plug 3 in for this original denominator, I also get 0. So the first thing we do is to directly plug it in. We get 0 over 0, which makes it indeterminate. So what we're going to do then is factor it. It's a nice quadratic. The numerator factors, the denominator factors, and thankfully they both have this common factor of x minus 3. So we can divide the numerator and denominator both by x minus 3, just kind of forget about it for now. That leaves us with a simpler function. It's the limit as x approaches 3 of x plus 1 over x plus 4. Now, the original function we have, what I have here in green over gray, is equivalent to the one that I have down here, x plus 1 over x plus 4. They're equivalent absolutely everywhere, except at x equals 3. At x equals 3, it's indeterminate, but everywhere else, we can evaluate it. So let's go ahead and evaluate it to the left of 3. Let's evaluate it to the right of 3. Plug it in. Plug 3 in for the numerator, plug 3 in for the denominator, we get 4/7. In other words, this function that I have right here, the x plus 1 over x plus 4, has a hole in it. It has a hole in it at x equals 3, but we still have a value of the limit from the left as x is approaching 3, and from the right as x is approaching 3. They're both approaching a y value of 4/7. I'm not exactly sure what it looks like, but I do know what's happening right there. They're both approaching that same value. And the next one, if you plug 2 in for x, you get another value of 0/0. So if you factor, you can simplify by dividing the numerator and denominator both by x minus 2. That makes this become the limit as x approaches 2 of 1 over x plus 4. Now when you plug 2 in, you get 1/6. So our limit is 1/6. So again, this is a nice simple graph. The original problem we have is equivalent to the simplified one everywhere except at x equals 2. At x equals 2, the value is undefined, but the limit is still approaching 1/6. It's just approaching it with a hole in it at that value. Another technique we're going to try is multiplying by a conjugate. So once again, you're going to plug in your value, plug 9 in for x in the numerator, plug 9 in for x in the denominator. We get 0/0, which is indeterminate, which means there's more work to be done. The denominator has the square root of x minus 3. We are going to multiply by the conjugate of that. In other words, we're going to multiply it by exactly this same thing, except the minus becomes a plus. So we multiply the numerator and denominator both by this square root of x plus 3. And what that accomplishes for us, especially in the denominator, is that when we multiply this square root of x minus 3 by its conjugate, do all the distributing, it just becomes x minus 9. No more square roots down there. The numerator, I'm not going to bother to factor it all out. I'll keep it, or excuse me, I'm not going to bother to multiply it out. We'll keep it in this factored form. Because now I notice that in the numerator, there is 9 minus x, which was originally up there, which is the exact opposite of x minus 9. I take this gray numerator, factor a negative out of it, so it's -1 times the quantity -9 plus x, which is simply x minus 9. So if we factor this gray, it's going to become -1 times the quantity x minus 9. So now we can divide the numerator by x minus 9, divide the denominator by x minus 9, and now our limit is this -1 I'm just going to put out in front of all of it. The limit is x versus 9 of what we have left over there, which is that square root of x plus 3. Plug 9 in, we can do direct substitution now. The square root of 9 is 3. 3 plus 3 is 6. Don't forget that negative sign out front. So when we multiply them, we get a value of -6. In our next example, the limit as x approaches 0 plus that's 0 from the right-hand side. So we're only considering a one-sided limit for this one. Like before, we're going to try plugging it in right away. That's always a good strategy. Always just plug it in first and see what happens. In this case, when we plug it in, we get 0/0, which doesn't mean it's impossible. It doesn't mean the answer is 0. It means there's more work to be done because it is indeterminate. So we're going to multiply by a conjugate again. This conjugate is a little more involved. I'm going to take this numerator. This is the one we're taking the conjugate of. we're going to multiply the numerator and denominator both by that exact same thing, but where that we have this -2, it's going to become +2. So we're going to multiply numerator and denominator both by that. Now, similar to what we did in the last one, we're going to multiply out the conjugates by each other. The square root of x squared plus 4 times the square root of x squared plus 4 is x squared plus 4. No more square roots. When you take the square root of something times its same square root, the square root sign drops off. When you multiply these inside terms and you multiply those outside terms, those are complete opposites. There's a +2 square root of x squared plus 4. There's a -2 square root of x squared plus 4. They cancel each other out. And then when you multiply these last terms, -2 times 2, you get -4. So here is the product of our numerator once we multiply those conjugates. Conjugates are nice because they get rid of radicals for us in this case. And in the denominator, I'm going to choose to do nothing right now because I've worked through a few of these. I kind of know what's going to be happening here. If I look at the numerator, which I've highlighted in that pink, compare it with the blue denominator, this +4, that -4, this cancel each other out. So it's x squared over the blue. If we divide the numerator by x squared, it's going to become x. And if we divide the blue denominator by x, it becomes this great term. Now, when you plug 0 in, plug it into the numerator, we get 0, and that's okay. But when you plug it into the denominator, 0 plus 4 is 4, the square root of 4 is 2, 2 plus 2 is 4. 0 divided by 4 is 0, that is okay. Our limit for this one is 0. And instead it's coming at it from the right-hand side. It turns out that we could have come at it from the left-hand side. I think our answer is going to be exactly the same. There's nothing weird going here. It's just slightly different notation. All right, next example. So you plug something in and you don't get a direct answer. You don't get the indeterminate of 0 over 0. You get some number over 0. So let's look at this first example. If we plug 3 in for x, you get 3 over 0. When I see that, it doesn't mean there's more work to be done with multiplying by a conjugate or by factoring. We're going to go straight to some analysis. In other words, let's look at what's happening with the y values as x is approaching 3 from both sides. So again, when we plug 3 into the beginning, it does not exist. You can't have 3 over 0. That doesn't happen. But if we plug something like 2.99 in, something just slightly less than 3, that would give us a numerator of 2.99, fine number. And then 2.99 minus 3 is 0.01. 0.01 squared is well, it's a very small number. And so now we have a relatively large number over a relatively small number. Like 3 isn't a huge number, but compared to its denominator, it's pretty big. And if I were to make it even closer, like 9, this numerator would stay pretty much the same, but the denominator is going to get even smaller. And the concept here is if you have a big number divided by a small number, you're getting a huge number. In fact, it's going to be approaching infinity. If you enter this expression into your calculator, look on the table as x values are getting closer to 3 from the left, and as x is approaching 3 from the right, numbers that are slightly bigger than 3, those y values are growing without bound. So the limit for this one does not exist, but it does not exist because it's getting infinitely large. So we're going to say our answer is infinity. Example to the right. So go through your process again, plug in the direct limit, you get 5 over 0. That's not indeterminate, it means there's some analysis to be done. So going down to our table here, plug 2 in for the function, it does not exist. You plug something in from the left, something in from the right, let's see what's happening. If you plug in 1.9, 5 divided by 1.9 minus 2, that's 5 divided by negative 0.1. If we divide that, we get a value of negative 50. If I put in 1.99 or 1.999999, a huge number, or not a huge number, a number that's getting very, very close to an x value of 2, but slightly less than that. So 1.99999 minus 2 would be something along the lines of negative 0.00, a bunch of zeros, however many you want. 5 divided by that, it's a relatively large number divided by a relatively tiny number, which means it's approaching infinity, but with the negative, it means it's going towards negative infinity. In other words, from the left, as x is approaching 2, the y values are going down without bound. And then from the right, if we plug in 2.000001, we get almost the same result, except it's going to be positive now. So a relatively large number divided by a relatively small number means we're going to be going up without bound. So this time, those two branches are diverging from each other. They're not both going up or down. They're splitting, so this one does not exist at all. We can't even explain how it's not existing. It just does not exist. Last example here is limits of functions with absolute values in them. So the limit of f of x of 5 over the absolute value of x minus 2, find each of the following. We're going to start off with direct substitution again, because it's going to be the simplest way to evaluate these limits if it's possible. If you plug 8 in, 5 divided by 8 minus 2, 8 minus 2 is 6. The absolute value of 6 is 6, so we get a value of 5/6. Not bad. Negative 3 minus 2 is negative 5. The absolute value of that is positive 5. 5 divided by 5 is 1. Our limit is equal to 1. Again, not a big deal. In letter C, now we have the big deal. As x is approaching 2. If we plug 2 in, 2 minus 2 is 0. Absolute value of 0 is 0. 5 divided by 0 is undefined. It's not indeterminate. It's undefined. We need some analysis here. So let's plug in something slightly less than 2, like 1.9. 1.9 minus 2 is negative 0.1. The absolute value that is positive 0.1. 5 divided by 0.1 is 50. I could get even closer and closer, 1.99, 1.999. These are going up without bound. We have a relatively large number divided by eventually some really, really small numbers that's going to be infinite. If we plug in 2.1, 2.1 minus 2 is 0.1. 5 divided by that same number is going to be a relatively large number divided by a relatively small number, which is going towards infinity. So this limit, as x approaches 2, is going to be infinity. One more example that's not in your notes that I'm going to have you try is the limit as x approaches 3 of 4 times the absolute value of x minus 3 over x minus 3. So to begin with, plug in 3, you get 0 over 0. Sounds indeterminate. Is there something we can do to factor this one? How do you factor an absolute value? Can you just cross it off? Can you ignore it? In this case, I would probably go towards the analysis again. Plug in something slightly less than 3. Plug in something slightly greater than 3. And see what happens. You can see the table that I have below, and you can see those values becoming different from each other. And because those are different, our limit does not exist. And this one, maybe a little more explanation might be in order. So if we look at a graph of this one, at x equals 3, it does not work. So we're looking at the graph of f of x equals 4 times the absolute value of x minus 3 over x minus 3. What would happen if I plug in something to the right of this limit, like something bigger than 3? Let's plug in 4. And the numerator, 4 minus 3 is 1. Absolute value of 1 is 1. 4 times 1 is equal to 4. And the denominator, 4 minus 3 is 1. So 4 over 1 gives us a value of 4. So when I plug 4 in, I got a value of 4. F of x, we plugged in 4, we got a value of 4. What happens if we plug in 5? 5 minus 3 is 2. The absolute value of 2 is 2. 4 times 2 is 8. Plug 5 in the denominator. 5 minus 3 is 2. 8 divided by 2, once again, is 4. Now, if I plug in another one, like 4.01 or 3.1 or any other number to the right, think about what's happening here. You're taking some number that's bigger than 3, subtracting 3 from it, so that value has to be positive. And the absolute value bar doesn't matter then, because the absolute value of a positive is just a positive. So we could say divide this by the exact same thing, because again, the absolute value bar doesn't matter. You get f of x equals 4. That's what's happening over here. From the right, the y values are consistently 4. But if we plug in something less than 3, like 2, okay? So 2 minus 3 is negative 1. The absolute value of negative 1 changes it to the opposite of positive 1. 4 times 1 is 4. And I'm going to plug 2 in for the denominator. 2 minus 3 is negative 1. 4 divided by negative 1 is negative 4, the complete opposite. So as I think about numbers that are less than 3, maybe like plugging in 2.9, plug in 1, plug in 0, plug in anything to the left of 3 for the absolute value. And when you subtract that minus 3, you'll get a negative value, and then you're taking the complete opposite of it. So in this case, when x is less than 3, the absolute value is really the opposite of x minus 3. So it's 4 times the opposite of x minus 3 over x minus 3. So then I could divide them both by x minus 3 again. 4 times that negative gives us a negative 4. So from the left-hand side, we have all these values that are approaching negative 4 coming at it from the left. At x equals 3, it doesn't exist. So from the right, from the left, they're divergent. They don't converge on the same number. So our value doesn't exist. It just does not exist.